Hello, good morning, good afternoon, good evening, everybody, wherever it might be. We are very delighted to have a speaker on site today. He came all the way from Aberdeen, EHUD MEIR, and he will tell us about geometric methods in braided vector spaces and Nichols algebras. EHUD, the floor is yours, the Zoom is yours. Take it away.
Thank you very much, and thank you for the invitation. So yes, this is a seminar in non-commutative geometry. I will tell you today about Nichols algebras and about how you can get Hopf algebras out of them. So maybe the starting point I would like to tell about will be something about Hopf algebras. So in the non-commutative world, we should think of Hopf algebras as sort of the structures that encode symmetry. And very much like that in the case of classical geometry, commutative geometry, we just have groups. Hopf algebras are kind of what is replacing groups when we speak about the non-commutative world.
I have a question.
Yes.
About the title.
Yes.
Do you really mean geometric methods or non-commutative geometric methods?
I mean geometric methods in the classical sense.
Classical sense.
Yes.
Okay.
So like really algebraic geometry, and I hope I will manage to get to them probably much later in the talk. It's
Excellent.
okay. So Hopf algebras. What kind of Hopf algebras we have? Well, so as we said, they come from symmetries. So some classical examples that we have is that let's say that I have G, which is a group. Yeah. Then I have the group algebra CG. Let's call this H. Now, let's just say what is the extra structure that I have on my Hopf algebra that takes it from an algebra to a Hopf algebra is that I have a co-multiplication delta that goes from H to H tensor H. How should we think about these things? So there are some axioms that we can write down. I just prefer you to think about it in the following way. Delta is a map that enables you to take tensor product of representations of H. If you have two representations of H, then the tensor product is naturally a representation of H tensor H. Pulling it back along delta will give us a representation of H. So when we speak about, for example, H, which is CG, well,
so only the co-multiplication will play a role.
I mean, also
the whole package.
yes, I mean, I'm going to think of it as an algebra plus co-multiplication such that conditions hold.
Yeah, but what about the co-unit, the antipode?
Well, the co-unit is uniquely defined once the co-multiplication is given. The antipode, again, is unique.
Yes.
Yes.
Okay.
So, I mean, I just prefer to kind of take it to the minimum. Not that the other structure is not important. It's just this way I can concentrate on this thing. Okay, so when I have H, which is CG, how would I take the tensor product of the representations? Well, I just have the diagonal action. It's encoded by the fact that delta of G, where G is an element of the group G, is equal to G tensor G. I would like you to notice that this is an example of what we call co-commutative. And by co-commutative, I mean that, well, the formula that I have here is invariant under the flip. If I flip the first and second terms of factors, I get the same thing. Okay, what other examples of symmetries we have in the classical world? We have Lie algebras. So let's say that G is a Lie algebra. Then, well, by itself, it's not an associative algebra, but there is a way to construct an associative algebra out of this. I can take the universal enveloping algebra. So I can take U G. So this is kind of the polynomial. I can think of it as the polynomial algebra on G with the relations that xy minus yx is equal to the commutator of x and y. How does the coproduct look like here? So here, instead of taking diagonal action, I mean, I still have diagonal action that is given basically by the Leibniz rule. So here I have the delta X is X tensor 1 plus 1 tensor X. And again, you can see that this is co-commutative in the sense that the order doesn't matter. I mean, it's invariant obviously. Another way to think about this is that if you have two representations in both cases, and you take the map V tensor W to W tensor V, which will just send me V tensor W to W tensor V, just the usual flick map, then this is an isomorphism of representations. Yes, I mean, in general, this is an isomorphism of vector spaces, but it's not clear a priori, and it's not always true that it's going to be an isomorphism of representations. In these two examples, it is correct, is the case. Okay, one more example I want to give here of this kind of co-commutative pop algebras. So we said that there are examples coming from a group, coming from groups. So we have group theory plane, we have examples coming from lead theory. And we can also consider the case of the interaction between the two things. So if I have, let's say, a group G that acts on some Lie algebra G, I also get an example that I will write like this. I can take CG and take something that I call the same direct product with U of G. So, I mean, this would just be as a vector space, CG tensor U of G. And when I say some direct product, I mean that I have the relation that Gx G inverse is going to be equal to G of X. And the co-multiplication would be defined as the product of the co-multiplication on the group algebra and the universal enveloping algebra.
Sorry, so probably by what you wrote in the last line, yes, you need the joint action.
Yes.
Okay.
Yeah, so I mean, like really I mean, G is an invertible element.
Yeah.
So I mean, I can also write it as Gx is equal to G of X times G. Yeah, so I mean, the action of the group G on the Lie algebra G come into play. Important thing for me to mention here, even though I use G to describe both things, it doesn't have to be the Lie algebra of this one. It can be like, let's say that this is a finite group and this is some crazy Lie algebra, whatever it might be.
As long as you have an action.
Yes, as long as there is an action, and there are many examples for this. Okay, so
G could be a Lie algebra of a normal subgroup.
yes. Okay, so in general, getting classification theorem in pop algebras is quite difficult. However, in this case, at least when we speak of things that happen over C or in general over an algebraically closed field of characteristic 0, this is really everything that we have. This is a theorem of Cartier, Milnomo, and Constant. So we have, let me write this. So we have a theorem from the 60s of Milnomo. Constant. Sorry. That over sorry. Over and then algebraically closed field of characteristic 0. Every commutative of algebra is of the form KG, semi-direct product U of G, where Kg is the group algebra of my ground field K. K is my ground field here. Okay, so important thing for me to say here is that both assumptions are quite essential. So both characteristic 0 is essential. Once you pass to characteristic P, things become more difficult, and also algebraically closed field is quite essential here as well. Again, when the field is not algebraically closed, funny things might happen. Okay, so this was kind of the commutative story.
Yes, in the positive characteristic, you don't even have a good notion of the Lie algebra. You can speak about an extended Lie algebras.
I mean, you have things like restricted Lie algebra. Yes,
Yeah.
that come into play. Then the universal enveloping algebra and also the universal enveloping algebra, you have quite a lot of examples. Okay, so this is what happens in the commutative case or co-commutative case. We are here in a seminar about non-commutative geometry. So let's see some examples of that are not co-commutative. So first thing, let's take G to be a finite non-abelian group. I can take K of G, and this is going to be the algebra of all functions f from my G to K. Okay, and this is spanned by the delta functions that I will call E sub G. Okay, so these are orthogonal idempotents. So I think of EG as the thing that takes 1 on G and 0 on all the other group elements. The co-multiplication here takes the form that delta EG, so the co-multiplication is induced from the multiplication on G. It takes the form sum of EA tensor EB, such that AB is equal to G. Okay, and as you can see here, since A, B, and B are not necessarily the same, this is something that is not going to be co-commutative for a general not Abelian G. Okay, some other examples I would like to show you. So most of the example I will show you will actually look very similar to the example that I have here, this semi-direct product of a group algebra together with a universal enveloping algebra. However, they will be only almost the same, which again is something that happens quite a lot in non-commutative geometry. I mean, we start with the commutative thing and then we kind of deform it. So first I would like to tell you about an example that is known as the Tufts algebras. Tufts. So let's do the following. Let's take n inside n, just an integer. I would assume that it's bigger than 1 here. I take zeta, which is an nth root of 1. And then I take the following algebra, K, algebra generated, associative algebra, not commutative, generated by 2 elements, G and X. Modular relation that G to the n minus 1 is 0, X to the n is 0, and Gx, G inverse, is equal to zeta X. So modulo the ideal generated by this field. Okay, so this algebra has dimension n squared, and we have kind of a canonical basis given by powers of G times power of X that do not exceed n, or n minus 1 even. And I should tell you what is the co-multiplication since this is a Hopf algebra. So for G, it's just going to be again, a group-like element. So we just get something like the cyclic group of order n here. So delta G is G tensor G. Delta X is a bit more tricky. It's X tensor 1 plus G tensor X. Okay, so instead of previously when I spoke about the Lie algebra case, I just had something like X tensor 1 plus 1 tensor X. This is what I usually is called primitive elements. And here I have what I call skew primitive elements. Okay, so skew primitive means that instead of I replace the one here by G, and notice that because I replaced the one by G, this is no longer co-commutative. When I do the flip, I get something that that's not the same. Okay, another example. So this was the Taft of algebras. Another example comes from the exterior algebra on a vector space. I think I might need another one. Okay. So second example would be, okay, so I take K, and now I take the thing that is generated by G, x1 up to xn, modulo the following relations. So xi square is going to be 0, xi xj plus xj xi is going to be 0. And G xi G inverse, sorry, not G inverse is going to be equal to minus xi. So I write it as in this way, like the sum of G xi G inverse plus xi is going to be 0. And finally, G square is equal to 1. So I have G square minus 1. Okay, this again has a very similar kind of flavor to it of how the co-multiplication looks like. I just have that delta of G is equal to G times of G. And delta of xi is xi tensor 1 plus G tensor xi. Okay, so again, I can think of this as sort of a semi-direct product. Again, this is only skew primitive. I can think of it as a semi-direct product of Kg acting on the algebra generated by x1 up to xn. And the dimensions here, by the way, are 2 to the n for this, because that's just the exterior algebra. The dimension of this is 2. Yeah, and in total, I get something of dimension 2 to the n plus 1. One more example, because we are here again in the noncommutative geometry seminar, is, I guess, the most famous example is, well, UQSL2, which again, you can also take to be a bit more fancy. You can speak about UQSLN or UQG. So the formations of the universal enveloping algebra. Let me just remind you how this looks like. So I have UQ SL2. So this is generated by 3 elements. Okay, I use a K for the field, so I will use something else like a G for instead of what is usually called K. So G to the plus minus 1, E and F. And the relations are, well, we have quite a lot of them. Let me just mention what they are. So I will just write it as equalities. It will be a bit easier. G inverse is equal to Q square E. G F G inverse is equal to Q to the minus 2 F. EF minus FE is equal to G minus G inverse divided by Q minus Q inverse. Okay, this is actually everything. There are some variations of this when I take Q. So this is for Q, which is a generic element of the complex numbers. If I take Q to be a root of unity, there are some quotients of these so-called small quantum groups that are also quite interesting by themselves. Yeah, point is, what I want to tell you about this is that, well, what is the co-multiplication? So I have, again,
These roots of unity are quite wild. These things at roots of unity are quite wild.
They are.
Go to some non-cosine-simple algebras and
yes, I mean,
quite a story in itself. Many miracles happen
I mean,
at roots of unity.
yes, I would say like there are some things that we can say about the representation, for example. I mean, it still follows the similar classification results to the algebra.
Well, like for instance, if you look at SLQ2, not UQ of SLQ, SLQ2 Hopf algebra, it's a root of unity, then this is a cross product of a classical Hopf algebra with some finite one. Oh. It's quite fancy.
So, I mean, some funny things. There are some things that do happen here. I mean, so the thing is, like, let's say this by itself is not going to be exactly same direct product like the previous ones were, but we are in a nice situation that we can kind of deform this relation in order to get something that is a same direct product. Okay, so I have delta J is G tens of E, and let me just mention that delta E is something very similar. I can take E tens of 1 plus G tens of E. And delta F is equal to F tens of G inverse. Plus 1 tens of E. So again, both of them are what we can call F, not 1 tens of F, 1 tens of E. The opposite 1 tens of F. Okay. Okay, so something that happens in, for these, all the examples, all the last 3 examples is that I showed you, is that even though they are not co-commutative anymore, they still have a property that kind of resembles co-commutativity, which is to say that all, wait, yes, am I?
Okay, we're asked to the board.
Yes. So all 3 examples are pointed. And any chance that, wait, point. That, which means that every simple co-module is one dimensional. Okay, so think about it like this. If we have, let's say, a finite dimensional algebra, then if it's commutative, then we know that every representation, every model is one dimensional. This is kind of a dual picture that if we have a co-commutative algebra, every co-model is one dimensional. What happens here is that it's still true that in these examples that every simple co-model is one dimensional, even though the algebras that I presented you here are not co-commutative. I mean, this condition is weaker than being co-commutative. Okay, and and also notice that in all the examples that I gave you here, the things that generate all these algebras are group-like elements. That is, elements that satisfies delta G is G tens of G, together with some, well, not really Lie algebra elements, but skew primitives. So we have the following. It's better. We have the following conjecture that was mostly studied by Luskiewicz Schneider, but also many other people, is that every pointed algebra is generated by group likes and skew primitives. Okay, I should be a bit more careful here. Every pointed finite dimensional. And also I shouldn't use this, so pointed finite dimensional.
So this is their counterexample, which is infinite dimensional.
Yes, it's actually quite easy to produce some. So it relates to it's going to relate to the question of finite dimensionality of Nichols algebras that I will mention very soon. But yeah, it is quite easy to put these examples in that are infinite dimensional. Okay.
Sorry, I have a question. Example of Hopf algebra which is not quasi-triangular, not pointed.
Wait, not quasi-triangular, not pointed. I mean, you can take functions on a finite group, on function on a billion group. That would be not yeah, that would be non-pointed because yeah, and it would also it's also not quasi-triangular because I mean you don't have a braided structure. It's not even true that V tensor W is always isomorphic to W tensor V. So this conjecture was studied quite a lot by Schneider and by Angiono and also by other people, including Ishmael Heckenberger, including many people around it. And here's the main result that they proved. So, Schneider and also they proved that true if the group of group-like elements, which I will write as G of H, so let me just write that it is, it's all G such that delta G is G tensor G is billion. So let me mention that there is one very minor paper by Schneider where they proved it in case all of the prime divisors of the group of group-like elements are bigger than 7. Because there are some funny things that happen when we have small prime divisors. Then Angiono finished it also for the case that there are divisors of prime divisor 2, 3, 5, or 7. Or the order of the group.
So these examples, these finite dimensional examples, you have this pointedness almost for free because you have only one.
Yes, so I mean, in this case, in the example that I wrote, yes. Okay, so I mean, I would say it's if I'm not mistaken, it's not so easy to prove. It's not so hard to prove that if you have something that is generated by like elements and discrete primitives, then necessarily it's going to be pointed. Yes, it's going to be pointed. I mean, but the other way around, that everything is pointed is generated by group like discrete primitive. That's more difficult.
Does it mean that there are some examples for group elements forming a non-abelian group, which is pointed?
For non-abelian group, which is
Yeah, it's a good question. Yes.
so can you say it again?
So this is the assumption that the group likes form a group, abelian group.
Yes. Yes.
What about examples?
So this
non-abelian examples.
Yes. So this is what I will talk about today. Actually, I will be quite. I will mostly concentrate on that. But I mean, it's kind of. I want to give some example in the abelian case because this is what I would say we understand the best. Okay, so the thing is, you might look at this thing and you will ask yourself, okay, how do we even approach such a question? So the starting point was to ask a kind of associated graded object. So the first tool that Nichols and Schneider used was to consider the radical filtration. Wait, co-radical. Oof.
I worked you.
Yes. Which is, I mean, I'm not going to define it exactly. I will just mention that here I have all the, I mean, the first level of this co-radical filtration is just, so group algebra of the group-like elements, kg of H. In H1, I also have the skew primitives. Then I have H2, which I will not tell you exactly what happens there, but it's kind of something that is dual to the filtration by powers of the Jacobson radical. When we speak about let's say, the dual Hopf algebra, which is going to be also finite dimensional Hopf algebra. Then what we can do is that, this is not a filtration of the HIs by themselves are not algebras, but they do satisfy that if I take HA and multiply it with something in HB, this is contained in HA plus B. And there is also some condition on the coproduct that I will not write here. But the point is that I can pass to the associated graded thing, which is what I call HGR.
Sorry, can you tell me what H2 is? Because it's nice H0, span of group likes and skew primitives. What is H2?
So think about it like this. I can take H. I apply a coproduct. I go to H tensor H.
Yeah.
Then I'm going to take. I hope that I'm not mistaken the indices, but I take H modulo H1 tensor H mod H1, or maybe H mod, I think maybe H mod H0 tensor H mod H1. And I take the kernel of all of these. And this is going to be my H2.
Okay.
Yeah.
Okay, thank you so much. Yes.
And I mean, you can continue. I mean, this.
Yeah. But because I asked this question because it also shows a pattern for higher numbers.
Yes.
Actually, H1 do not consist of skew primitives. There are some primitives together with
a group of primitives. Yes.
Yeah.
Which is kind of, I mean, in H1, it's like I go to H mod H0 tensor H0, and then, everything
that is inclusion.
Yes.
the first quotient of this option.
Yeah.
Skew primitive.
Then the idea is that I can pass to the associated graded thing, which is HER, which is the direct sum of H n mod H n plus 1, H n minus 1, H n minus 1 for n, which is bigger than or equal to 0. This filtration ends, which is kind of given to the statement that the Jacobson radical of a finite dimensional algebra is always important. Okay, so I have this filtration, and I get this new Hopf algebra that I call HGR, and what is possible to show is that this thing is already a kind of semi-direct product. It's KGH, semi-direct product with some algebra A. The thing is that I need to understand what this A is. Okay, now I also prefer to use a slightly different symbol. Instead of using the semi-direct product, I use my favorite thing, hashtag. It's usually referred to as a bosonization or Radford byproduct of these two things.
Yeah, and now you're associated with Twitter and.
Oh yeah,
Associated with Twitter and
of course.
social media. Hashtag, yes.
The A here, so I should say, is so in the previous cases, it was kind of I said what was it as an algebra, but the beauty of this is that this A is actually a Hopf algebra, but inside a different category. Not the usual thing as a Hopf algebra in vector spaces, but it's a Hopf algebra in what is called the Yetta-Drinfeld modulus over G. So it's usually written like this, GGYT. Okay, and then it's a very
G is G of H. G is G of H.
G of H, yes. Yes. G is G of H. Okay, and then it boils down to the question, what kind of Hopf algebras we find inside this category? Of course, I still didn't tell you what is this category, so I should tell you what it is, which I will do in a moment. Point is that here we get the Hopf algebra that is really this kind of the local algebra. It has a unique model and a unique unique simple model, unique simple co-model. And comes the question, what kind of?
I assume that A is determined uniquely
Yes,
by this,
yes.
but how?
So how is it determined? So I have a map from HGR because I have a direct sum decomposition now. I have a map of Hopf algebras from HGR onto H0 that splits the inclusion. And then I kind of take A as sort of co-invariance of algebras to the. I mean, once I have a splitting with respect to a group algebra, I can define this A and show that it has a structure of an object in this.
You have a collection of KGH, and you have invariance of this collection.
Yeah, so I mean, the idea is to, okay, I have a map onto H0, so I can, like, if I call this thing HGR, I can look at the HGR going by delta to, I hope I'm not mixing the sides here, I just might, so I apologize if I do. But I can do this, I take first delta to HGR tensor HGR.
Projecting onto K.
Yes, and then I get to HGR tensor H0, which is, as we said, it's just KGH. Okay, but then I can ask what are, so this gives me a coaction of H0 on this, and I can ask what are all the things that that are co-invariant under this, and this gives me exactly this. I can show it's a subalgebra. And then I'm going to, the thing is, it's not a sub-coalgebra, but I can modify the coproduct so that it will be sub-coalgebra. This is exactly the point where what previously was Q primitive all of a sudden becomes primitive. Okay. So how am I doing with the?
Excellent. So
Yes.
in 27 minutes, use 4 slides. So we are safe.
Oh yes.
You will not exceed
I'm not going to.
30 slides.
Okay. Very
Because
good.
now there's a limit of 20 screens we bumped into it during the summer semester. But to go over 20 screens, your speed would have to be better than 4.5 minutes per slide. And you are doing like 6-7 minutes per slide.
Okay. Yeah, so that's good. I mean, I usually I think I speak a bit too quickly, so it's actually good that it keeps me a bit.
Yeah, it slows you down perfectly.
Okay, so let's see. We get that what we have now is that HGR is this KG hashtag A, as we said before, and this A is graded. And we also said that it was a Jeter-Drinfeld is in GGYD. Okay, so I would like to tell you first something about this category, about this Jeter-Drinfeld category GGYD. So what are the objects here? So objects here are, well, V, vector spaces that are graded by, first of all, graded by G. So V splits as the direct sum of V sub G, where G is in G. And I also have a G action. G acts on V.
That was just G coaction.
Hmm?
That's just a G coaction.
That's the G coaction, that's the G action, and they should be compatible with one another. So I would like that if I act with G on the H homogeneous component, this shouldn't be the same as V sub H. So V sub H is usually not a sub-representation, but it should be VGHG equals. Okay, so here's one nice thing about this, beyond the fact that again it is again a monoidal category. I can use the way that I tensor multiply comodules over Kg and how I tensor multiply modules over G to also get a tensor structure on this thing. The nice thing is that I also get a graded structure. So, I mean, I kind of told you in the beginning that for co-commutative Hopf algebras, V tensor W and W tensor V are isomorphic via the usual flip. In the general case, they are not, but in this category, I do have what I call a braiding. that goes from V tensor W to.
But you always have it. It doesn't have to be such a particular group ring of algebras.
No, but I would like to concentrate on
Okay.
this particular case.
And I just want to make sure that it's clear to everybody. Braiding comes from heterogeneous structure. You don't need this particular form of algebra.
It's just that it's easier to write, but so I mean, the thing is, if I take, let's say, V inside V sub G and W inside W, so how does it look like? The braiding will take V tensor W. So previously I would take it to W tensor V. But now I want to consider also the gradient of V, so I actually take it to G of W tensor V, where the G comes from the grade of this particular little v. Okay, so this gives me a braided structure. I can still say that V tensor W is isomorphic to W tensor V. In the general case, it's not symmetric. If I go from V tensor W to W tensor V to V tensor W again, I don't get the identity. That complicates things. Okay, and then, as we said, we have a graded algebra here. And moreover, let's just,
Boundary conditions.
sorry about that. And I also have the property that it's connected, by which I mean that A0 is equal to K, just a ground field. This is a result of the fact that the original algebra had all of H0 inside degree 0. But then I take kind of this semi-direct product of KG with A, and A does not remain in degree 0. I only get the ground field. And then the original question about being generated by group-like elements and skew primitives kind of translates to the question, the new question. Does A, or is A, more precisely, is A generated by primitive elements?
Is this equivalent to generating by A1?
Yes, wait. In a more general way, yes. It's just that the thing is, if you have an A, so let's say, I mean, everything in AY is going to be primitive. So if I know that A is generated by A1, then I know it's generated by primitive elements. However, it gets a bit tricky because if, like, let's say I have an example that is generated in degree 1, but I also have primitive elements in degree higher than 1, I can take the dual algebra and then I get a counter example. So it's quite a tricky thing. Okay. So the question is, let's say that I just know that A is a finite dimensional graded Hopf algebra inside this category, and I know that A0 is K, so it's connected graded. Do I know that A is generated by primitive elements? And I would like to give one more formulation of this question. This is the point where Nichols algebras come into play. So, and again, what I will tell you now, I only need a braided monoidal category. I don't need specifically this braided monoidal category, but it's we need to start from somewhere. I guess these kind of categories are the easiest to deal with among the braided monoidal categories, who are not just, let's say, vector spaces or super vector spaces. Okay, so if, let's say, I have V inside this category, G, G, Y, D, then the first thing that I want to tell you about is that I have TV, just the tensor algebra on V. This is the direct sum of V tensor N is bigger than or equal to 0. This has an algebra structure which is just as exactly what you would expect. I mean, V tensor A times V tensor B goes to V tensor A plus B. However, this is also a Hopf algebra. And maybe it's important thing to say here is that I really use the braiding when I describe Hopf algebras inside this category. So usually the most, let's say, difficult axiom for Hopf algebras is the fact that multiplication is a map of algebra. So co-multiplication is a map of algebras, also known as multiplication is a map of coalgebras. In order to say what that means, I need to use some kind of braiding. I need to be able to move two copies of the same vector spaces one by the other, and I need to use the braiding. So a Hopf algebra inside this category is not the same thing as a Hopf algebra inside usual vector spaces. This is kind of the point where things change a bit. And kind of taking the same direct product with KG is a way to resolve this issue, to get the Hopf algebra inside vector spaces. How is this thing T of V? How is this a Hopf algebra? Well, I just declare that delta of V is V tensor 1 plus 1 tensor V. So V tensor 1 plus 1 tensor V. Yeah, so just the primitive elements, and I extend by multiplicativity. Okay, so I mean, and the idea is that if I want to calculate what is delta of, let's say, V times W, I need to take delta of V times delta of W, then I need to multiply them, but upon multiplying, I will have to use at some point this kind of braiding. This is the thing that will make things much more complicated. Okay, and then comes the question, as we said, so do we really have all the primitives in degree 1? So, well, in principle, the way that I define it here, it's quite possible that I will get some primitives in higher degree in some way or another. I will give some examples in a moment. Okay, but there is something that we can do about it. If I have primitives in higher degree, then they would form a Hopf ideal. I can divide by this Hopf ideal. If now after dividing by the Hopf ideal, I still have some primitives in higher degree, I can divide by them again and again and again and again. So,
And here they are using finite dimensional.
I mean, this is not finite dimensional.
Yeah, but in this argument.
Yeah, I mean, it might take infinitely many steps a priori. I mean, I also the result in algebra. So, yeah. So dividing iteratively by primitives in degree bigger than 1. We get what they call the Nichols algebra. B of. And this algebra, okay, so again, it's going to be a Hopf algebra inside this category. And it has the property that, so V of V is generated by V. So this is V of V is graded. And the primitives of V of V are just the elements of V that they started from. Okay, and in fact, these three conditions, they define the Nichols algebra. So if I have a Hopf algebra, and okay, of course, I should say V of V is connected. So V of V 0 is equal to K. So these conditions together, they define the Nichols algebra in the sense that if I have an algebra satisfying all of these, necessarily it's going to be the Nichols algebra. Okay, so, and then again, a reformulation of the question that we had before is every connected, graded connected. That connected neck head A inside GGYD a Nichols algebra. Okay, so is it the case? Graded connected, and I forgot, I usually forget it. Finite dimensional and Nichols algebra. So just to give you an example, if I even take something like the tensor algebra, it's not a Nichols algebra. It's also not finite dimensional. Okay, so it's the reduction to this question is not completely trivial, but I prefer not to go there. I just want to tell you that this is kind of the thing that we are looking at. And because of this, one quite important question is, well, what are the finite dimensional Nichols algebras? Let's say I start with GGYD. I have many objects. I mean, I know how to classify the simple ones. I can ask for what simple ones and also for what direct sum of simple ones do I get something that with the finite dimensional Nichols algebra. So
Did you tell us what Nichols algebra is? No.
I did, but not very explicitly. I mean, so I told you that you take the tensor algebra, you divide out by the primitives in higher degree. You divide out by the primitives in higher degree. I have no primitives left.
Okay, for me, this was the definition.
Yeah, I mean, this is one definition. There is also another one, but let's see if I have time for it. I would like to give you some concrete examples of what we get and how we get some classical things like symmetric algebra or exterior algebra. So let's first take the example. Let's take V, which is inside 1 YD. So I just take I take G to be the trivial group. Okay, and then I mean something graded by the trivial group is a vector space. Something with an action of the trivial group is also a vector space. So it's really is just the category of vector spaces. There's nothing here beyond that. In this case, let's see what we get. So if I calculate, let's say, a delta of VW, and I mean I'm talking here now about what happens in the tensor algebra of V. Then I will get V tensor 1 plus 1 tensor V. W tensor 1 plus 1 tensor W, which will give me VW tensor 1 plus 1 tensor VW plus two more things. I have V tensor W plus W tensor V. Okay, but what happens? So this was for delta VW. It's not primitives because I have these two things, this V tensor W and W tensor V, that kind of destroys the chance of being primitive. But then what happens is that if I consider delta of WV, this is going to look very similar. So this will be WV tensor 1 plus 1 tensor WV plus, again, W tensor V plus V tensor W. I mean, this follows just by doing exactly the same calculation as we have here. What do we learn from this? We learn that VW minus WV is actually primitive. And therefore, in the Nichols algebra, this is going to be 0. So at least in characteristic 0, what happens is that these are the only relation that we need to divide out to get to the Nichols algebra. So in that case, we get that P of V is equal to just the symmetric algebra on V, which, well, is infinite dimensional. Okay, let's take another example. So we gave one example with the group of order 1. Let's take one with the group of order 2. Okay, so let's take V inside not G, sorry. CT, and Y, D, and I write CT as generated by an element G. And let's say that V is equal to VG. And G of V is always minus. You can check that it really defines yet a Reinfeldt model that it satisfies the condition. I mean, simply because, I mean, if V is VG and G is the only conjugate of G, there's not much to verify here. The braiding here is given by the map that sends V tensor W. Because of this action that G of V is minus V, this will go not to W tensor V, but to minus W tensor V. Then when we try and calculate what we get for the Nichols algebra, we get something very similar. We get that VW, in this case VW plus WV is primitive. And from this we deduce that the Nichols algebra in this case is just the exterior algebra on V.
And in general, you have like VW minus the braiding of.
Of course not. So in general, that's the point, that it really is very tempting to say that, probably I divide out by VW minus C of V tensor W, but no, but in general, it's going to be much more difficult.
Okay.
So here is one example so in both these cases, all of the relations that I have were in degree 2, right? Like VW plus WV or VW minus WV. Let's see one more example. So I take V to be a span of V. Okay, so just a single element. I mean, this will be now in Cn Y D. Again, Cn is cyclic of order n, generated by some element G. And again, V is just Vg. And G acting on V is going to be zeta V, where zeta is an nth root of 1. Okay, again, it's possible to check that we get yet a Reinfeldt model. And notice that now it's only one-dimensional.
Do you want it to be a primitive root or not necessarily?
Primitive, yes. Yes, thanks. Okay, so V tensor V now will map to zeta V tensor V. Here's what we get for the Nichols algebra in this case. So we get that V of V is equal to, well, it's just going to be polynomials in V, K of V, modulo V to the n. Okay, so we do get something which is finite dimensional of dimension exactly n, the n that appears here. Yeah, so BV is just a truncated polynomial algebra. And the reason is that we can kind of, we have this kind of trick that when we look at the delta of V is going to be V tensor 1 plus 1 tensor V. And because of this weird commutation relation that we have that really consider the braiding, I get that V tensor 1 and 1 tensor V commute only up to zeta. That means that when I raise it to the nth power, I just get the sum of the n power of both things. V to the n is primitive, and I need to divide out by this thing. Okay. Okay, so that kind of what happens is that when we consider the case of, let's say that the group is abelian, then things continue to be in this spirit, but of course they become much more difficult because we don't have only one cyclic group and only one element, but we might have bases of different things. So we get what we call groups of diagonal type. So we get the braided vector spaces. So if G is abelian, we can show it using the fact that every representation of an abelian group, every reducible representation of abelian group is one-dimensional. But basically, we are going to have some basis for V. V1 up to Vn, such that the Vi tensor Vj, not Ci. Oh. Okay, so Vi tensor Vj maps to Qij, where these are some scalars, non-zero scalars. Qij, Vj tensor Vi. Okay, and then comes the question, okay, so when does it happen that these things are finite dimensional? And this question was studied by Bish von Heckenberger. And okay, so not only he did quite deep, profound work in classifying all of them, part of this classification program that I mentioned before of Andruszkiewicz and Schneider was also to show that, yeah, that if something is finite dimensional, then necessarily it's a Nichols algebra. So the idea was to really to study when do we get finite dimensional Nichols algebras, and then to show that if we have a finite dimensional algebra, all kinds of relation needs to hold, and then showing that if something satisfies these relations, it's already a Nichols algebra. And this is very much the story of what happens in case the group is abelian. I would like now to tell you about what happens in case the group of group-like elements is not. There are quite some funny things that happen. Okay, so now that I know that I'm up to time, I allow myself just to skip to the next slide. Okay, so let's ask what happens when G is not abelian. Okay, and I would like to give you some concrete examples. So let's say I take G to be equal to Sn, the symmetric group.
Yes.
And letters.
I expected you to do it.
Do you know what V I'm going to take? No. Okay, so I'm going to take V to be the span of elements that I call Xij. Or Vij, but I already wrote X, where I is less than J. And I is at least 1 and J is at most N. So really all tuples. Yeah. And the braiding, so okay, the V of Xij. So I mean, I need to tell you what the homogeneous component that lies in, and this will just be the transposition Ij, which makes sense. I mean, they form a single conjugacy class inside Sn. And okay, I should tell you what is sigma acting on X Ij.
Sorry, I don't understand. The degree is what, a number or what is it?
Now this is N. Or to say it in other words, I mean Xij, they are inside V Ij. Like the Ij homogeneous component. Because V is braided by a string.
Yes.
Okay, and sigma of Xij is going to be -1 to the sigma, so the sign.
Is it a transposition or a conjugacy class of this transposition?
It's a transposition,
Okay.
like a specific transposition Ij. Sigma Xij, I just act by conjugation and I also add the sign sigma, so this is X. And I will write it like this, sigma Ij, sigma inverse. Okay, so basically, I mean, I have a basis parameterized by all transpositions, and yeah, this is how the action of the group looks. Okay, so we might ask, do we get here a finite dimensional Nichols algebra or not? So here's an example of something that happens. Let's take the case n is equal to 3. So in this case, we have 3 transpositions, 1, 2, 2, 3, and 1, 3. And I get K, I will write it like this, A, B, C. The relations are A square, B square, C square, so they all square to 0. And I also get AB plus BC plus CA. And I also have AC plus CB plus BA. And you can show very much by hand that this has dimension 12. You might wonder what happens when I get n bigger than 3. So let's write a small table. So when n is 3, and then I have the dimension of B of 3. Okay, so here I have 12. 4, I have 576.
Right, so we are describing V, right?
I mean, up to here, this was B. This thing here is B of 3. Yes. So I mean, I already take the tensor algebra and I divide that by primitives in higher degree, which in this case, they're all degree.
This is Nichols.
Yes. So for degree 3, I mean, you can pretty much use kind of combinatorics and kind of non-commutative Braided basis to show that dimension is 12. It's not very big. Dimension 4 is more difficult. It's 576. Dimension 5, it's 8,294,400. And the number that obviously you all expected. And for 6 and above, it's not known. We don't know if it's finite dimensional or not. Yes. So, and this is because, and think about it, this definition of the Nichols algebra, I mean, non-commutative algebras are very difficult. I think we can all agree on that. And the Nichols algebra is given in such an implicit way that these kind of things happen, unfortunately.
Sorry, so also for n equal to 6, you have a similar description. And relations.
So that's the thing. I mean, I have a similar description. I understand the relations. We understand the relations in degree 2. We don't understand if there might be more primitive elements coming in higher degree. If I just take the analog relations in degree 2 and I divide out by them, I get what is called the Fomin-Kirillov algebra, which appears in algebraic geometry in some other contexts. But it's not even so clear if these are the only relations or not.
Okay.
I should also mention the first one to describe this, I mean, to find out the dimension is 12, are Milsky and Schneider. Okay, so this in this case, what I would like to tell you about today, and this is mostly, and this is comes to converging slowly to what I've done with Istvan and Leandro.
So you're about to begin your talk.
Yes, I mean, it's, you know, after 1 hour and 7 minutes, it's, I should have done it at some point. Okay, I want to give you some specific example that we studied, and to tell you how we've done it. So, okay, so here I spoke about what happens. So first I mentioned abelian groups, then I mentioned Sn, which are almost simple groups. Now let's take an example of solvable groups. Okay, so let's take the following group. G is generated by 2 elements x and y with the relations that y to the p is 1, x to the a is 1, and xy, x inverse is y to the p. I should give some more context here, I guess, so that, as you would imagine, p is prime. And what I have here is just a same-direct product of a cyclic group acting on another cyclic group. So y is cyclic of order p, x is cyclic of order a. And yeah, you just conjugate y to some power of y, that is this y to the p. Okay, and I'm going to, my v is going to be span. I'm not going to say exactly how it comes from this, but no, I will say probably. So it's going to span by EI, where the degree of EI should be some element of the group. So this is going to be x to the I times y, which, by the way, form a single conjugacy class. I'm going to tell you the braiding here. So the I terms of Vj, or now we get confused because we wrote here Vi instead of Pi. Let me. Okay, so AI tensor Ej. I'm not going to describe the action, but you'll have to believe me that this is what we get. We get that AI tensor Ej maps to -1. Vs again E Bj plus 1 minus 1 minus B I tensor Vi. Again, it should be E, not V. So it's started writing the.
Shouldn't be this -1 raised to some power?
No, it's just minus this one, just -1. Yeah, okay. Because these are just like what happened for 2 x.
Wow.
Okay, and I mean, this thing I will, so the resulting thing V, I will just write it as the, what they call the affine thing, the affine space with parameters B and P and P. Notice that A doesn't satisfy that much of a role here. A is just the order of B in the multiplicative group Z mod P star. Okay, and again, there is the question of what kind of, do we get here finite dimensional Nichols algebras or not? So here's the thing, here's a list of things that happen, of cases where it is finite dimensional. So if we take f3, 2, this is actually exactly the same as the example before, the S3 example. And we get something of dimension 12. Then we have 5, 2 and 5, 3. And in this case, we get again something finite dimensional of dimension 1280 in both cases. Okay, that was 2 and 3. Then for 7, we have 2 more things that are finite dimensional. So we have f7, 3 and 7, 5. Again, because I really like to cite big numbers, both of these are dimension 326,592. Okay, and the theorem that we have proved, so it's
Sorry, so these are dimensions of what?
of the Nichols algebra.
Nichols algebra. Okay.
Dimension of the Nichols algebra, because I mean the dimension of the vector space themselves is just 3 or 5 or 7. The dimension of the Nichols algebra will so the
Here.
B of V. This is what means. So this is theorem of Heckenberger. Yeah, I cannot seem to. Sorry about that. Heckenberger.
Right, so then is it correctly, the dimension of this vector space, the second number, right? Like,
So the second number is the B that appears here.
so what's the dimension of V when I see this affine 3, 2, 5, 2?
So the dimension of V is 3, and then 5, and then 7.
So it's the left.
Yes, because I have a basis given by EI, and okay, the I think maybe I think I made a mistake here. It should be x times y to the I. Yes. Because this way I really get P elements. I can really get P elements. That's my point. Yes. So theorem Heckenberger.
Okay, thank you. Yes, yes, yes. Okay.
And we proved that these are all the finite dimensional ones. Not 5 final. Oh, what's going on? Finite dimensional one. Actually, we proved something a bit more general, is that if you have a Jeter-Drinfeld module, which is of dimension P, and some condition holds, like that the support of the module generate the entire group, and it's irreducible, then necessarily, again, it's one of these five.
Sorry, so these means these.
These five.
Yeah, but these are all the finite dimensional ones among
Construction. Yes, among FPB.
okay.
Yeah, I mean, we actually proved something slightly more general, which is if we have a Jeter-Drinfeld module over a group G, and this Jeter-Drinfeld module is irreducible of prime dimension, and the support of V generates the entire thing, then necessarily it's one of these five, but nothing beyond that. So in general, the way to think about it is that having a finite dimensional Nichols algebra is something quite exotic. It's if you just like randomly pick a braided vector space, most likely that the Nichols algebra will be infinite dimensional. I mean, think about the case that we mentioned before, where we have something one-dimensional and V tensor V goes to Q times V tensor V. For this to be one-dimensional, we need Q to be a root of unity. But this is really like a group of measure zero inside a complex plane. So it's very specific to say that we get something finite dimensional.
But you do have examples of finite dimensional Nichols algebras not coming from this construction.
Yes. So, I mean, for example, all of the abelian groups cases that I mentioned before, the one done by Heckenberger and Ruskevich, Schneider, okay, so on. And also the ones coming from Sn, like for n is equal to 3 or 4 or 5. These are also.
Why this construction is so interesting?
It's kind of
The motivation for this construction, to considering Nichols algebras coming from this construction.
Well, because it's kind of this, I would say it's the simplest case where we have something that is not abelian, but still very close to be abelian, in the sense that this is a solvable group. It seems to be that there are quite a lot of things that are known in case that we are dealing with a simple group like almost simple group like the SNs from before. But again, all problems are quite difficult, I would say. So, and this is something that we know how to say.
What is the degree of nilpotency of this group?
Mm-hmm.
What is the degree of nilpotency of this group?
Just two steps. It's not nilpotency, but solubility. Because it's an extension, it's an extension of cyclic group by cyclic group.
Okay, thank you.
So it's the closest thing to be an abelian.
Yes, very good.
But not abelian, that we can hack for. Okay, so in the remaining time I have left, I would like to tell you how we prove these kind of things, and this is the point where, as I said, geometric methods are going to come into play in this field. So next question is how? Okay, so first of all, I should tell you how do we think of these things in a geometric way? So, well, let's say that I have a V, which is a braided vector space. Okay, not necessarily something that comes from a Jeter-Drinfeld module, but some braided vector space. So a vector space together with a map C from V tensor V to V tensor V that satisfies the usual what is called the Young-Baxter equation. Or in other words, the braid relation when we have 3 tensor copies of V. How would we describe such a thing? So, well, we can think of this as we can just pick a basis of V. So let's say V is the span of EI. And then I can say that C of EI tensor EJ is equal to the sum. Well, this is a linear map, so I can always write it with some numbers. CIJKL, EI K tensor EL. Okay, And then when I want to say that it satisfies the Young-Baxter equation, the Braided equation, it's just another way to say that CIJKL satisfies some polynomial equations. Okay, so I can look at Z, which is the set of all CIJKL. And I will not write the exact polynomial equation, but I will just write it as conditions. Okay. So what happens here? So, okay, now comes the question, is it really true to say that any point in Z is the same as a Braided? Almost. There is an issue here that the particular number that I got here, this CIJKL, they depend on the particular choice of basis that I made here. So what happens here is that I have an action of GLN given by a choice of basis, and the different orbits, they correspond to different isomorphism types of braidings. Okay, so orbits is going to be the same as isomorphism types. Okay.
So
Yeah.
what is n in relation to these indices I, J, K, L? Are they running from 1 to n or?
The dimension of B is n. Yeah. Dimension of B is.
Okay, so these are, okay, so n is the. But this is just a bunch of numbers.
Yes, and that satisfy the condition to make
But it lives in a vector space of what?
of dimension n to the 4.
Okay.
The 4.
And this is on what you act with GLN.
Yes. So it's, I mean, if you think of it, it's like it's going to be the representation V tens of V tens of V dual tens of V dual.
Okay.
And
So you wrote that it is a set.
yes, it's actually, so it's a heuristic closed subset. More precise, yes. So it's, we can think of this as an affine variety, the way that, yes.
Not a scheme.
We can also think about it as a scheme, but I mean, I only have 8 minutes left, so I prefer to think of it as affine variety. So let's just say that
It can happen that you have nilpotency.
if you,
A ring.
I mean, there is the issue that if you just take the equations that come, then yes, maybe you will have nilpotence and you will. But let's really talk about it as just as an affine variety, just to make things a bit more concrete. Now, here is something that might happen. So in a perfect pole, what happens is that all of the orbits, the GLN orbits inside Z are closed. And then I am in a situation where I can describe kind of the quotient space, like the space of all solutions to the Young-Baxter equation just by invariants. Here's something that might happen. I mean, it is possible that I will have one orbit, let's say like this. So I will call it O1. And then I will have another, and it will not be closed. And I will have another orbit in its closure. So now I will use different color. We'll have this thing that appears on the boundary, which I call O2. Okay, why is it important for me, specifically for questions of Nichols algebras? Because having a finite dimensional Nichols algebra is something that will descend to from O1 to O2. So in principle, if we are in the situation that I have one orbit on the boundary of another one, and let's say I take some C prime in this O2 and I take C inside O1, then the dimension of BVC is going to be bigger than or equal to the dimension of BVC prime. I should say what I mean by BVC and BVC prime. So far I kind of took for granted the braiding that I have. But the Nichols algebra depends on the particular braiding. And if I have two different braidings on the same vector space, then I need to mention what braiding I actually used. Okay, so one possible strategy to prove that something has a an infinite dimensional Nichols algebra is to look at this. show that this has infinite dimensional Nichols algebra, and deduce that this one has an infinite dimensional Nichols algebra. Now, what's the problem with this is that if we take the examples we mentioned before of the affine FPB, all of the orbits are closed. Okay, so unfortunately, the orbit, I will just write it as O of PB are closed. Okay, well, what can we do when the orbits are closed? So allegedly it looks like we're kind of in a dead end here, but here's the thing. We can use also reduction mod P, then all of a sudden the orbits that weren't closed, that were closed before become non-closed now. So how do we do reduction mod P? So we have the following observation. I mean, all the examples that I gave you here, all the structure constants, it was something like EI, tensor EJ, let's recall it, maps to, I want to be precise here. I don't, BJ plus 1 minus B, minus EBJ plus 1 minus BI tensor EI. All of the coefficients here, all the CIJKL are just going to be -1 or 0. Okay, so that means that all the coefficients are actually in Z. And if it's in Z, I can reduce it mod P, and I can ask what happens in characteristic P. Okay, so this is all defined over Z. And then we can reduce mod P. And once we reduce mod P, all of a sudden the orbit is not closed anymore. So we found a specific deformation to show that how to get from this O1 to O2 to some orbit, the boundary. P, so and then the O.
Is P arbitrary?
Hmm?
Is P arbitrary or?
No, it's exactly the same P. Yes.
Mhm.
Yes. O FPB is not closed. Okay, so we pass to the orbit on the boundary. Once we pass to the orbit on the boundary, each one that knows way more Nichols algebras than I do just said, this is something that I know from the diagonal type case, from the abelian group case. And he knew to say exactly when is this thing finite dimensional and when is this thing not finite dimensional. So the result was that, okay, and then the only cases that it was finite dimensional was the 5 cases that I mentioned before, like when P is 3 or 5 or 7, and B is also quite specific, like 2 or 3, and also 5 in case.
Okay, comes back to Z after this reduction.
Oh, so here's another nice thing is that if I look at I have a braided vector space over the complex numbers, let's say, that is actually the braiding is defined over Z. And then I have V, and then let's say I have some kind of, I will call it a lattice defined over Z, which I can then take the reduction mod P. Yeah? So again, if I take the dimension of this Nichols algebra, of this thing, this is actually less than or equal to the dimension of the original. And then this by itself was bigger than what I get for the smaller orbit on the boundary. And then I get that, okay, for the smaller orbit on the boundary, I get an infinite dimensional Nichols algebra, then this is infinite dimensional, and this is infinite dimensional. I should say that here the dimension is, as we said, over C, and here the dimension is over filled with P elements, FP. But I mean, nevertheless, it's okay. Dimension is just a number, so it makes sense to compare it between the two. Okay, I think my time is more or less up, so yeah, I think it's a good place to stop, and thank you very much.
Thank you so much. He used 11 out of 20 euros.
Okay, so not so general.
I told you. All right, any questions? Maybe first, anybody from Zoom? Thomas, how about you? You do Hope Algebras? Okay, no volunteers from Zoom to ask a question? Well, then how about Warsaw? Anybody?
I have a silly question about the permutation group case, because if you could come back to the slides where you had the table
Yes.
dimensionality.
Yeah.
Well, that's up. And
Yeah, this one.
yes.
I know it's maybe a silly question, but are there any dependence on the dimension of V and B of V? Because first thing that came to my mind was that, okay, all of them are squares, and it seems that there is some connection between the next ones, because 576 is 12 times 2 squared. And
Yes.
the other one, you have to, if I remember correctly, multiply by 576 by 5 and then take a square.
Okay.
And because you have n equals 5, it's kind of suspicious, but it's too small of a sample for me to even say that, oh, that may be interesting. So I decided to ask whether that is known.
I mean, so in fact, I must admit that short answer is that I don't know enough to give a good answer, but I tell you what I know. And the thing is that it's not only that the dimensions are known, but also like the Hilbert function is known. Because remember that this is graded. And what happened is that the Hilbert functions, for a reason that I'm not sure now, is always going to be of the form, product of things of the form 1 plus t squared plus t to the a minus 1. Like, let's write it as t to the ai minus 1, and I take a product. Let's say I goes from 1 to some a. Okay, so I mean, it's going to be a product of these kind of things, the Hilbert function. And then when you ask what is the dimension, well, then it's going to be the product of the AI. The reason that, I mean, at least in the case of the things of diagonal type, when the group is abelian, I know that what happens is that it really generalizes the Lie algebra case in the sense that you have kind of a finite PBW basis. Okay, so and then PBW basis, but all of the basis elements they are nilpotent, and that's the reason that you get just 1 plus t squared up to the nilpotency degree. And then you get something like this. So the reason that you get this kind of thing is that you have, I mean, also all these numbers, they decompose nicely into prime numbers, and the reason that it happens is that really it's a product of these things. But to say exactly why it's a product of these things, that I am not so sure.
It's still much more than I ever expected asking this question, so thank you very much.
So it wasn't the stupidest.
Yeah, basically it was not.
Yeah. Anybody else, Tomek?
Yes, so is there some conjecture in terms of this Hilbert function, what you obtain for n equal to 6?
I don't know. I mean, I think it's, as far as I know, I might be wrong about this, but as far as I know, there isn't a conjecture about what the dimension here should be. It's just conjecture that the dimension is still finite, but I don't know if there are expectations to what exactly it should be.
So this Hilbert function, the shape of this Hilbert function is not systematic enough to raise conjecture.
And not that,
Well, yeah.
not that I'm aware of, at least. Maybe yes. That's not about it.
Okay.
Okay, so are we good to wind it up?
I have another question. So So this Nichols algebras is a step for the reduction of more general question
Yes.
about this
Generation by,
translation.
yes.
You are passing to this associated graded.
Mhm.
Okay. So what can you get from your analysis
Well, so
for this initial question?
for this initial question, let me think, so I'm pretty sure that we get that as long as we can get results such as long as the group is of this particular form. So I mean, basically the problem that might happen is the following. So I mentioned that when you form the Nichols algebra, you take the tensor algebra and then you start dividing out by primitives, and you divide more by primitives, and then in the end you get the Nichols algebra, and maybe it's finite dimension. Here is something that we don't want to happen, but might happen, is that maybe after dividing out by some of the primitives, but not all of them, you already get something which is finite dimensional, but still not the Nichols algebra. You need to divide a bit more to get the Nichols algebra. In that case, you will be able to get a counterexample to the original question, like about generation by group primitives and group-like elements. If I'm not mistaken, in this particular case of like the FPB, it doesn't happen. Because again, I mean, we know classification of all the finite dimensional ones, and we more or less know how how it looks like. That is, I mean, we know what are the primitives we should divide by.
So all this adventure was failed attempt to find the counter result.
So I mean, it's that's kind of the thing. It's like you need to try to find a counterexample, and you also don't want to find a counterexample, which
You don't want to find it.
yes, I mean, so like personally, I would hope that this conjecture is true, that it is always generated by.
Still, this construction is rather peculiar. This construction is rather peculiar.
The Nichols algebra.
No, even more than F, P, and E.
Let me try and answer this. So the thing is that we have a classification of the of simple objects in the Yet-Drinfeld category in this GGYD. And the idea is that and it's basically given by you choose a conjugacy class, single conjugacy class in the group G. This is because, I mean, we have this G of VH is VGHE inverse. So we fix the conjugacy class on which it is supported. And then we need to take an irreducible representation, not of the entire group, but of the centralizer of a given element in this conjugacy class. And this was the place where this FPB came from. It's like it was picking specifically the conjugacy class of X, which is all the elements of the form X times Y to the I, or Y to the I times X. And picking an irreducible representation of X itself. Of the centralizer of X, which is the group generated by X. This is where the sign -1 came from. So I would say it's more like going systematically over the things that we have. And so there is another theorem that I didn't mention, also by Istvan Heckenberger and Leandro Vendelmin, where they show that in most cases, if you take direct sum of the things, like V direct sum W, and V and W are both not of dimension 1, most likely the Nichols algebra will be infinite dimensional, unless some specific things happen. Yeah, but then it's and then it really reduces the question to understand what happens to the simple models, the simply Yet-Drinfeld models, and that was kind of a specific case to start from. Again, with a group that is already not abelian, but it's not as complicated as simple groups, or almost simple groups, like I say.
May I ask another question?
Yes.
About this Poincaré-Birkhoff.
Yes.
Did I understand it correctly that you are talking about some extension of this PBW or?
So there is, at least in case that the group is abelian, there is a kind of Poincaré-Birkhoff theorem, which says something like, okay, I don't remember exactly what are the conditions, but at least in case the algebra is finite dimensional, the idea is that we have a basis, let's say x1 up to xn, such that, let's say that xi to the ai is equal to 0. This is the potency degree of big psi. Then you will have a basis that is given by things of the form x1 to the n1 up to xm to the nm, and I is somewhere between 0 and ai minus 1. So in this way, you generalize the Poincaré-Birkhoff. So you really get this kind of basis.
Okay.
Yeah, the Xi's are exactly the fact.
Poincaré-Birkhoff comes from some understanding, some theory. Do you have this theory behind it?
Yes. Yes.
What is this theory?
Okay, so let's think about like this. In the Poincaré-Birkhoff, what you do, I mean, you use the fact that you have this commutation, like xy minus yx is equal to the commutator. So whenever you have things in the wrong order, you know how to get them in the right order plus things of lower degree. And here, actually, I mean, you need a bit more. You need also to okay, so the idea is that you really, I mentioned before that you get this kind of matrix Qij of all the structure constants that you get. These are all roots of unity, and more or less they're going to look like you take some Cartan matrix and you take you raise it to the power of you take some root of unity zeta, you take zeta to the power of Cij, where Cij are elements in the Cartan matrix. Then you really have a complete top algebra, Lie algebra that come into play. And a lot of the things that happen also including the relations that you have that are, so I mean, you have this kind of relation called the Serre relations. And they generalize to something called the quantum Serre relations, where instead of just commutators in the usual sense, you get like quantum commutators, which you can think of as the formations of
Quantum commutators of which sort?
So
xy minus what?
xy minus qyx.
Yeah, I missed.
Xy minus qyx.
Very good, thank you.
Okay, so let me ask the final question, more philosophical than mathematical.
Okay.
So I'm used to point to the algebras giving some very strong results in Hofstadter theory. This is why I appreciate them.
Okay.
But how about Nichols? Why do we bother? Why do we care about Nichols algebras?
Well, from every Nichols algebra, you get automatically a pointed one.
Aha.
You get automatically because, I mean, I can just take this kg, as we call it, hashtag B V,
And that's point.
and that's pointed. Okay, so everything that you do with pointed is
Okay, I've got you. Okay, so let us thank you again for a very beautiful talk. Thank you. Let me stop recording.